Welcome. Today we are tackling the challenge of differentiating hyperbolic functions when they are defined implicitly. Unlike standard functions where y is isolated, implicit equations weave x and y together. Understanding this process is vital for solving complex problems in physics and engineering where these curves naturally occur. Hyperbolic functions describe the shape of hanging cables and the motion of waves. Often, the relationship between variables isn't a simple function. By mastering implicit differentiation, you gain the power to find the rate of change at any point on these sophisticated geometric paths. Before we begin, remember your core hyperbolic derivatives. The derivative of sine h is cosine h, and the derivative of cosine h is sine h. Notice there is no sign change like in circular trigonometry. We must also apply the chain rule whenever the inner argument is more than just a single variable x. Our strategy follows a consistent four-step process. We differentiate the entire equation term by term, apply the product and chain rules where necessary, gather all terms containing dy or dx on one side, and finally factor and solve to isolate our derivative. To solve for dy or dx, we divide both sides by cosh of y. This gives us dy or dx equals 1 over cosh of y. This result tells us the rate of change at any point on the curve, expressed in terms of the vertical coordinate y. Visually, as y increases, cosh of y also increases, which means the fraction 1 over cosh of y becomes smaller. This matches our graph, where the slope of x equals sin of y flattens out as we move further from the origin. Now let's try a more complex example, cosh of y plus x times y equals 10. Here, the second term is a product of two variables, x and y. We must use the product rule, derivative of the first times the second, plus the first times the derivative of the second. Differentiating term by term, the derivative of cosh of y is sin of y times dy or dx. For the term x times y, the product rule gives us y plus x times dy or dx. The derivative of the constant 10 on the right side is 0. Next, we move all terms that do not contain dy or dx to the right side of the equation. We subtract y from both sides, leaving us with sin of y times dy or dx plus x times dy or dx on the left, and negative y on the right. Now we factor out dy or dx from the terms on the left. This isolates the derivative into a single factor multiplied by the quantity sin of y plus x. We are now just one algebraic step away from our final answer. Finally, divide by the expression in the brackets. Our derivative dy or dx equals negative y divided by the sum of sin of y and x. This expression allows us to calculate the slope at any point, x, y, that lies on the original curve. Consider a more advanced case involving the hyperbolic tangent. Here, the argument is a circle equation x squared plus y squared. This will require nested applications of the chain rule as we differentiate the inside of the tan function. The derivative of tan is sec squared. We keep the inner argument the same, then multiply by the derivative of that argument. On the right side, the derivative of x is simply 1. Let's expand the derivative of the inner quadratic expression. Differentiating x squared gives 2x. Differentiating y squared gives 2y times dy or dx, again applying the chain rule because y is a function of x. We now have an equation where dy or dx is embedded within a set of parentheses. To isolate dy or dx, we distribute the sec squared term to both parts of the addition inside the brackets. This separates the term with our target derivative from the term that only contains x and y, allowing us to move it to the other side. Subtract the term without dy or dx and then divide by the coefficient of dy or dx. The result looks complex, but it follows the exact same logic as our simpler examples. We have successfully found the derivative for a nested implicit hyperbolic function. What happens if the denominator of our derivative is 0? In our previous example, if 2y times sec squared of u equals 0, the derivative is undefined. This indicates a vertical tangent line on the graph at that specific point. The most common mistake is forgetting to multiply by dy or dx when differentiating a term with y. Remember, you are differentiating with respect to x. If the variables don't match, the chain rule must produce that dy or dx term. Another frequent error is carrying over signs from circular trigonometry. In hyperbolic calculus, the derivative of cosh is positive sin. Don't let your habits from sine and cosine lead you to add a negative sign where it doesn't belong. To summarize, treat y as a function of x, apply the chain rule to every hyperbolic term containing y, use the product rule for mixed terms, and use algebra to isolate dy or dx. This process works for any implicit equation, no matter how complex. Keep these derivatives in your permanent toolkit. Hyperbolic functions behave predictably, and implicit differentiation is simply a matter of careful bookkeeping. With practice, you'll be able to navigate these equations with confidence. Try this: find the derivative of sin of y equals x squared. Differentiating gives cosh of y times dy or dx equals 2x. Solving for dy or dx, we get 2x divided by cosh of y. Great job today! Generated by Vision Solve AI.